axis. So those are the ones in our graphic on either side. And then the one in the middle is your traditional horizontal axis wind turbine. And the reason we're going to use these vertical axis turbines is they have a much lower startup speed, so you don't need a huge amount of wind to collect energy. They also capture wind in all directions, which is good for us, and they're small and much cheaper. So we can build them for hundreds of dollars instead of millions. We can place them in small pockets of artificial wind. So now our research question. Our research question is, through computer modeling and field research, how can TMAW develop a predictive model for optimally placing a small-scale vertical axis wind turbine for cost-effective energy generation in varying artificial wind environments? And we think that by using our model, we'll be able to determine where to optimally place a wind turbine in varying environments of artificial wind, in a position where the turbine will be able to collect and store a sufficient amount of energy for long-term economic and environmental gains. So essentially what we're talking about here is we believe that the source of artificial wind, there's enough energy in there to merit putting turbines to capture this energy. And what we're really going to look at is where can we place our turbine in these areas of artificial wind to maximize power output. And we're hoping that by maximizing this power output, we'll be able to see financial viability, right? Because if the turbines don't make sense from an economic standpoint, no one's going to invest in them. You'll never see wide-scale adoption. So that's something that's very important. So now I'll hand off to John, and he will go through our methodology.
All right, so our methodology is basically split up into two phases. The first phase is our modeling preparation, and our second phase is real-world applications. So for our first phase, for modeling, we're using ANSYS Fluid in order to create simulations of cars moving on roadways so that we could find optimal places to place these vertical axis wind turbines. This part of the project is still under progress. However, we already have completed our preparation phase, which is building anemometer arrays. Anemometers are basically wind speed measurement devices, and our anemometer array consists of three, one at 3 feet, one at 3 feet, one at 6 feet, and one at 9 feet. So then, after our preparation and our modeling, we move on to preliminary testing. First, we have to calibrate our anemometers. We did this in the engineering wind tunnel, and we tested them from 5 to 30 miles per hour, from 5 to 30 miles per hour and 5 mile per hour increments. First we would set up our calibration rig in the wind tunnel, then we number anemometers, so that way we could keep track of which of the graph in each one. And then we compare it to the commercially available anemometer, which was provided to us in the lab, and repeat the process for each anemometer. Here's a little video showcasing how we went about this. So then you would set the wind speed at the little box there, and then it would blow out that wind speed, and then we could basically test to see if our anemometers are accurate or not. So then after anemometer calibration, we would move on to parking lot testing. So for parking lot testing, we would set up the site. We position the anemometer array in the middle. We would set up the site of the Comcast parking lot. We position the anemometer array in the middle of the parking lot, so that way we give our vehicles the maximum amount of time to speed up and slow down. We would also assign different positions to each member of our team. We'd have a driver, one who's driving the car, a co-driver, someone who would take the speed of the car as they're driving by, so that way the driver doesn't have to pay attention to the speedometer. We'd have someone who'd operate the anemometer array, so that way they could read data. And then we'd also have a spotter, so that way we can find out how far the car is as it passes the anemometer array. And then we'd have somebody in charge of safety, so that way we'd make sure, because we're driving at high speeds, so then we want to make sure that nobody interrupts us or gets injured. So, oh yeah, and for our anemometer array, here's our breadboard for our anemometers. So then we want to prevent ghosting for each anemometers. Ghosting is basically when one anemometer array would get one reading and the other anemometers would get the same reading. So in order to prevent ghosting, we implemented this circuit schematic. And here's our LabVIEW interface. So then it would give us the speed, wind speeds in real time, and it also graphic wind speed versus time, and we could also record the data into text documents. And here's a video of us performing our parking lot tests. Here's us using our mentor's pickup, very nice. And then here's a view from the co-pilot seat, just so you get the feel of it. And then here's another car we used, just a regular sedan. And here are results for our parking lot tests. We found that basically how we analyze the data is we would look for spikes to see basically when the car would pass the anemometer rate. As you can see, there's not really any definitive data for this. All this is mostly due to ambient wind. So basically we concluded that artificial wind produced by moving cars is very negligible compared to the ambient wind. So considering that you could say our results were very not inconclusive, but rather negative, we decided to move our project into more general directions, which we'll talk about later. So then for our phase 2 real-world applications, we would like to model other areas of artificial wind, such as the DC Metro, different forms of architecture, airports, and so on. And then for part 2, we would also like to develop a software package, so that way we could find the wind speed velocity profile of specific areas. And then using these two parts and these two pieces of data, we would be able to find the optimal places to place these vertical axis wind turbines. Now I'm going to pass it off to Jason to talk about our challenges.
Okay, so far we've had two main challenges, the first of which is in our communication with the State Highway Administration. We originally planned on putting anemometer arrays on the side of roadways to get data from real world traffic, but in order to do this you need permits from the State Highway Administration because putting a foreign object on the side of roadways is a safety hazard. We've been in communication with them for about the past year, but they haven't been very responsive. It usually takes them about a month to get back to us by email, and they don't usually say anything. So it's been a year later and we still don't have a permit. We're hopeful we can eventually get one, so towards the end of our project we'll be able to do real world testing on real roadways. We've also been having software difficulties with the fluid dynamics software. Fluid dynamics is a pretty complicated subject. It has lots of equations and the software is no different. So far we've been able to make basic shapes and upload our vehicles, but the software itself is too complicated. I know on my laptop it just crashes whenever I try to do something because the software is complicated. Okay. Our anticipated challenges in the future involve the inconsistencies in natural wind formation. Natural wind can change very easily. In one spot, natural wind can be different than 10 feet away or 10 feet up. In addition, in different places in the world, natural wind can differ. Something that might work in Chicago where it's very windy might not work in a not windy place, so there's a lot of inconsistencies there. We also anticipate future bureaucratic communication problems. As John said, we're going to make our project more general, which means we need to contact different groups such as the Metro and the College Park Airport. And we're hopeful that they'll be more communicative, but we have to be prepared if they're not. We also anticipate more problems with the software and hardware. We're trying to get more powerful computers to use right now, but we have to be able to prepare in case we can't or in case the software still doesn't work on these more powerful computers. Okay, so our conclusion is that we're trying to create a computational software model to examine the fluid dynamics in artificial wind generating environments in order to identify the areas of maximum wind speed. We will then use this model to determine the best location to place a vertical axis wind turbine and whether placing one there is both economically and environmentally feasible. Currently, we've done basic preliminary testing, we have basic data, and we are in the process of making our model in the fluid dynamics software. So our advice for freshmen, number one, is that communication is key. You should talk about your project. If you have an idea, you should mention it to your project. A non-communicative group will go less smoothly and less quickly than a communicative group. You should also keep each team member accountable. It's really not good for team dynamics if a few people aren't doing anything or a few people are doing everything. Everyone should be doing an equal amount of the work. You should also eat together because you're going to spend 3 years with the people you're working with, so you become friends. get to know each other, to make your time as enjoyable as possible. You should also be flexible with your project. We started originally just with cars on the side of roadways, but when we found out that that might not be viable, we expanded it to a more general project, which goes to the next point about you should fail early if you're going to fail. Like, you might think you have a great project right now, but for whatever reason it might not work. You don't want this to happen your senior year when you're scrambling to get your thesis done. You want it to happen as soon as possible so you have time to adjust. You should also become involved with your Gemstone project. This past summer I went to a conference at the University of Amsterdam. It was a great experience. The university paid for it. It was awesome. And the reason was because I got involved in my project outside just going to team meetings and got the most out of the Gemstone program. We would like to thank our amazing mentor, Mr. Brian Quinn, our librarian, Ms. Zeta Diaz, the UMD Department of Transportation Services, the Gemstone staff, and everyone that showed up here today. We're almost done, so we can always go home. So, any questions?
So you're talking about the wind energy, but to what extent do you think that you're going to get power out of this? Like, what are some practical things, like of the scale that you're looking at in terms of the power being produced by research?
One of our original plans was like streetlights, things like that. Like, not, we can bring power into the grid, but we can also power individual things with this. Like, you have a turbine for a streetlight, the turbine can charge a battery and power up the streetlights. I know that there was past tests with vertical axis wind turbines where the start speed, it's not that high, it's only like 8 miles per hour. So, like, cars going by, you should be able to reduce that and charge up a battery to like power things such as a streetlight or bring power into the grid.
What increase in wind do you need in order for it to be worth implementing the vertical axis wind turbines in places as opposed to just the ambient wind and the power that is
One of the articles I read said they tested vertical axis wind turbines just on like the side of the house, and it was able to like power the appliances, but it was only a few miles per hour more needed like at a time for a start speed, because wind speed in relation to power is a cubic function. So a little bit of wind, extra artificial wind, could do a lot in terms of helping with the power generation. It was able to power the appliances in a house, so a little extra wind should be able to power things such as streetlights or EV or active grid.
So, given your setbacks and whatnot, we struggled with getting the road test to really produce reliable results. But clearly there was, lit review, background that relates to that. So, in a theoretical way, like, how much can you actually get from cars going down the road?
Well, that's something we really don't know because it's highly dependent on the environment. So our theory, our sort of hopeful theory, is that in the parking lot it's wide open space. So you're going to see little or no wind on the side of the cars, whereas like on an embanked highway you might see a lot more. So honestly, we really have no idea at this point. That's why we're doing our fluent model. So once that's working, then we'll be able to see sort of qualitatively, what kind of wind we get in what environments.
But other people aren't doing that testing yet?
Not so much that we found. No.
I was just wondering why you're picking up the metro, because I feel like there's just not much energy to get there. Because when I'm standing on the platform, the only time there's ever really is when the train's first coming in. So that's like a few seconds of energy generation, and it just sits there the rest of the time.
Yeah, that's a good point. One of the good things about wind energy is that the fuel is free, right? So with traditional power generation, your fuel cost is the vast majority of your operating cost is fuel. With a wind turbine, the fuel is free. It's just there. It's not being used by anything. So even if it took a long time to sort of make your money back, and even just with little pockets of wind here and there, it might be worthwhile. We don't know yet, so.
The other reason why we're looking at the metro specifically is because, as we've said, these models are extraordinarily challenging to model the boundary conditions. That's why we've said the lit reviews are not consistent. There's no one who can model specifically a certain stretch of I-95, for example. But a metro tunnel, well, that has very significant solid boundary conditions because it's a circular tunnel or a square, rectangular tunnel, whatever. that would make our modeling easier, and that would make us more able to look at what other people have done, which is still not particularly a particularly large base of research, but that body of knowledge would then be more applicable because we have a very easy to understand set of conditions to look into our model and to model that way.
If you're testing in outdoor environments, what if instead of artificial wind, would you start cars being set back with natural wind? Could you restart those surveys?
Well, yeah, that's one of the sort of the big problems we face is it's very difficult to isolate what's the artificial wind and what's the natural wind. To be honest, in certain circumstances, it may not matter, right? Like if the embankment on a highway is sort of like an architectural structure that creates channels of wind, when you stick the turbine there, you don't care where the wind comes from, you just care that it's there. As far as our modeling goes, it's a little more complicated, obviously. So yeah, that is a challenge, isolating artificial wind. But as far as power generation, like once the technology is there, then, I mean, it just collects wind. It doesn't, discern between artificial and